From our earlier work looking at average slopes and then exchanging those with limits to be able to compute an instantaneous slope or a speed in the position versus time graph we looked at earlier, what we've done is actually created a very general, formal way to compute slopes at points. Previously, if we talked about a slope of some line, it would have to be between two separate points, and now we've got it down to a single point. And that's actually going to be our definition, or one definition, of the derivative. The slope at a point on a graph, with the slope itself, the value of that slope, we're going to call that value the derivative. Now, how do we compute it? Again, it's always going to be this ratio of rise over run. So it's always the same idea of a slope back when you had 2 points, rise over run, but with the addition of a limit. And that limit is always going to take the denominator, the run, the x range, down towards 0. So it's as if we only had a single point instead of 2 points. And there's a number of ways we can formalize this. I think most students feel most comfortable with this second one here, where if we have a graph and we pick 2 points and there's a delta x difference between them, what we're going to do is shrink the second point back down towards the first and make that distance get closer and closer to 0. And then the 2 points that we have are, say, c and c plus that delta x. So our closer point is c, our next point is c plus that shift, and the distance between them is delta x. And what we do is just compare the rise, the f values, over the run, the difference in x values. Sometimes h is used as sort of a generic catch-all. It could be time, could be x's. Some people don't like deltas, I guess. H is a very commonly used letter for these calculations in most calculus textbooks. Another way to do it as well, though, is not to think of it as c plus a delta x. We can actually think of it as some fixed point c, some later point x, and then what we're going to do is let x get closer and closer to c. So you have to really look at the small print here, literally the small print. Here and here is the same expression going to 0. The denominator itself is going to 0. In this version, you've got your 2 points, one of which is thought of as moving, one of which is thought of as fixed. The c is fixed, the x is moving, and the x is moving towards the fixed point c. So you may encounter these in different forms over the years, but they all represent exactly the same property. They're just different notations of convenience depending on how people are thinking about the relationship of the 2 points in the rise and run calculations. Let's do a quick example. So we're going to use that definition to find the slope of the function y equals x squared at the point x equals 2. So what we have here is f of x is equal to x squared. Never hurts to have a little perspective on the side. That's our classic parabola, x and y. We're going out to 2, and there's going to be some slope at that point. We are interested in knowing the slope of the tangent line at x equals 2. Well, how are we going to do that? What we're going to do is fix our attention on the point 2. We're going to have f of 2 involved. And we're also going to move out by, let's say, delta x. I think most people like that best. So we're going to have the point at 2 and the point at 2 plus that distance. And then we're going to find the difference in y values. That's our rise. And we're going to divide that by our run. And we just said, well, these 2 points are delta x apart. So we're going to have a delta x there. And then we're going to ask what happens to that expression, to that ratio, as the interval shrinks towards 0. Again, we can't just plug in delta x equals 0 because then we get dividing by 0 and that would be bad. But we can simplify. In particular, we can now use our function. So here's our function, x squared. Whatever's inside here is what we're going to call x. And we can put that inside our function. That's our input to x. We're going to square it. Then we're going to subtract f of 2, which is 2 all squared divided by delta x. And then we're going to take the limit as delta x goes to 0. We're going to need to expand this a little bit. So we'll have 4 plus 4 delta x's plus delta x all squared minus 4 all over delta x. So expanding the square and noticing that 2 squared is 4. Again, we can't just sub in delta x equals 0 yet, because we still have this delta x in the denominator. But we can, if we notice here we got a 4 and a negative 4, we can cancel those out. And then we have 4 delta x plus delta x all squared over delta x. And then we notice now that every term has a delta x in it. So this has 1 delta x, this has 2 delta x's, we'll take 1 away. And that will, remember we have to divide it through for every term. That'll leave us with a new expression. Delta x goes to 0 of 4 plus delta x over 1. Actually, we're done there. So now, in the previous step, we could not sub in delta x equals 0 because we had the denominator being 0. Now that we've canceled out the denominator, now we can just sub in delta x equals 0 to take that limit. And of course, when we do that, we simply get 4. Okay, what should that mean? That should mean that the slope of y equals x squared at the instantaneous point x equals 2 must be 4. Must be exactly 4. This value we just calculated, going back to the top, was the rise over run of 2 points, and the 2 points are getting closer and closer together, and then we calculated the slope based on those 2 points. The final value we got was 4. We can confirm that by looking at a very detailed computer-generated graph here. So here we are at x equals 2, y equals 4, and what we should be able to do is go over, let's say, we'll go over 1, and then we should go up to 6. That would be slope 4. And we'll do it on this side as well. We'll go over by 1. Oh, sorry, that's by 0.5. So we should go up to 5. We'll go over by 0.5 this way, and if it's slope 4, we should go down by 2. That'd be down to here. All right, we'll try to do this exactly. Not bad. I'll try one more time just to narrow it down a bit further. There we go. So we can see that at the point x equals 2, by having a line with slope exactly 4, that is what we get as a tangent line to the graph of y equals x squared. This graph here, if we ask what the instantaneous slope is at x equals 2, we get a slope of 4. And we got that in the previous page from a direct calculation from a rise over run and a limit. That's our definition of the derivative. Here's an interpretation of it on the graph, and that's going to be what we're going to explore for the next at least 3 units in the course. What can we use this derivative for, and how do we compute it?